Lesson 26, Models of the Atom. Part 1, Historical Models of the Atom. Over history, our understanding of the structure of the atom has changed quite a bit. In the 1800s, we started out with the billiard ball model of the atom. This model was developed by John Dalton in 1808. He said that matter is made up of atoms. Atoms are the smallest unit of matter, and they are indivisible. This means they can't be taken apart into smaller pieces. Atoms of each element are identical. This is the foundation of modern atomic theory. We know now there are some problems with this model. We know now that atoms are made up of smaller particles, electrons, protons, and neutrons. We also know that atoms of an element don't have to be identical. We have things called isotopes. For example, carbon-14 has 8 neutrons and carbon-12 has 6 neutrons, but they're both. The next model of the atom is the plum pudding model. It was developed by J.J. Thompson, who discovered the electron in 1897 and then proposed the plum pudding model based on his discovery in 1904. He said the atom is made up of positive material with negative electrons embedded throughout. It looked a bit like plum pudding. The model was abandoned when Rutherford discovered the nucleus a little bit later. The Rutherford model. Ernest Rutherford discovered the nucleus in 1909 in the gold foil experiment. Rutherford said the atom has a very dense, positively charged nucleus in its center. The nucleus is surrounded by electrons revolving around the nucleus like planets around the sun. Rutherford quickly acknowledged the deficits in his model. Electrons are in centripetal acceleration when they travel in circular orbits, and as an accelerating charged particle, they should constantly emit electromagnetic radiation. As they emit this electromagnetic radiation, the electrons would lose energy and spiral into the nucleus. In other words, if Ernest Rutherford was correct about his model, the Rutherford atom should implode, and it shouldn't exist for even a second before it's destroyed. Next was the Bohr model of the atom. Developed by Niels Bohr, he proposed the energy level model of the atom in 1913 after studying the emission and absorption spectra of elements. He said electrons can only have specific, exact amounts of energy. He called these energy levels. Different elements have different energy levels. If an electron absorbs a photon, it will jump up to a higher energy level. If an electron emits a photon, it will fall down to a lower energy level. Bohr's model didn't take into account the wave-particle duality of the electron discovered by de Broglie a little bit later. And there was no reason given for the fixed energy levels. The de Broglie model of the atom took into account the wave-particle duality of the electron. Louis de Broglie proposed the wave-particle duality of the electron in 1924. The electron energy levels are energies at which the electron can form a stable standing wave. If the wavelength isn't able to reach all the way around, the electron won't be able to exist in that energy level. If the wavelength is such that it goes around and then a little bit before the wave is completed, the electron would cancel itself out, and as a result it cannot exist in that energy level either. It's only energies for which the electron standing wave perfectly is able to complete itself around the nucleus where the electron is able to exist in a stable state. The de Broglie model of the atom worked best for hydrogen. It could not be used to explain multi-electron atoms beyond this first element. Our current model of the atom is the Schrödinger model of the atom. It is developed by Edwin Schrödinger, who published a paper detailing the Schrödinger wave equation in 1926. This is the wave equation. It's quite complicated and involves a lot of calculus. The wave equation predicts the probability of finding an electron at a particular place and time around the nucleus. Energy level shapes are defined as clouds of probability and are different for each level. The probability cloud is darker in places where the electron has higher probability to be located and lighter shaded in areas where it's less probable to be found. There are no problems with the Schrödinger model yet. This is our current atomic model. Perhaps the only great problem with the Schrödinger model is it's quite abstract and hard for modern students of physics to understand. Now that we've summarized the historical models of the atom, we're going to look in detail at several of the major discoveries in atomic physics that led to some of these models. We'll start with the discovery of the electron. Dalton's billiard ball model was the accepted atomic model for most of the 19th century. It was believed that the atom is the indivisible smallest unit of matter. In 1897, J.J. Thomson discovered the electron and showed that there were smaller particles within atoms. The atom is not the smallest unit of matter. He discovered the electron in his cathode ray experiments. The first cathode rays were experimented with in 1859. At the time, scientists had no idea what these rays were. Cathode rays appear when a cathode ray tube, or a CRT, is connected to a strong voltage source. A beam of looks like light flows from the cathode to the anode and can be produced by metal electrodes of all kinds. We now know that these cathode rays are streams of electrons traveling from the cathode to the anode. Thomson experimented with these cathode rays and found that unlike light, these rays would bend in the presence of a strong magnetic field. Ørsted's discovery in 1820 said that moving charges produce magnetic fields. Moving charges become magnets themselves. Since the cathode rays bent in the presence of a magnet, they must contain moving charges, since they're affected by this magnetic field. As a result, Thomson was able to determine that the cathode rays were not light. They were some kind of exotic particle that hadn't been discovered yet. The Thompson experiment. Thomson created a special cathode ray tube with an adjustable magnetic and electric field inside. This allowed the cathode ray tube to act like a special kind of mass spectrometer. The cathode rays were affected as they traveled through the magnetic and electric fields, and the results could be measured. The experiment was done in 2 stages. Step 1 was measuring the velocity of the cathode rays. When an electric field and a magnetic field were adjusted so the forces were balanced, Thomson could calculate the speed of the cathode rays. This is also the principle behind a velocity selector on a mass spectrometer. The electric force came from the electric field. We know that the electric force on an electron is equal to Q times the electric field. In this case, because the electric field lines point down and electrons travel in a direction opposite to the field lines, the direction of the electric force is up. The magnetic force comes from the magnetic field. The magnetic force is equal to QV times the magnetic field. The direction of the magnetic force comes from the third-hand rule, in which our fingers point in the direction of the magnetic field. Our thumb points in the direction of the particle's velocity, and the palm of our hand tells us the direction of the magnetic force. We use our left hand because these are negative charges. The direction of the magnetic force, according to the third-hand rule, is down. If the electron beam is to travel through the electric and magnetic fields undeflected, the forces are balanced. This means Fm equals Fe, or QVB equals QE. Q appears on both sides of the equation, so we can cancel it out. We can rearrange this for V. The velocity, when the forces are balanced, is equal to the electric field strength divided by the magnetic field strength. This is how you calculate the velocity of anything traveling through a velocity selector undeflected. In the second step, Thomson calculated the charge-to-mass ratio for the electron. When Thomson turned the electric field off, only the magnetic field remained. Using the velocity he found in the first step, he used the radius of curvature for the cathode beam to determine the charge-to-mass ratio for the cathode ray particles. The velocity was now known based on the work he'd done with the velocity selector stage. The radius was measured, so it became a known value. and he was looking for the charge-to-mass ratio. He was looking for the charge-to-mass ratio because he had no way of knowing the individual charge or the individual mass, but he could find how they related to each other. He used Fm equals QVB, and Fc, the centripetal force, equals mv squared over r. When the particles travel in a circular path, the magnetic force is equal to the centripetal force. QVB equals mv squared over r. V appears on each side of the equation and can be cancelled out once. Then we can rearrange for the charge-to-mass ratio. Q over m equals V over BR. This is Thompson's equation for the charge-to-mass ratio of an electron. Again, he wasn't able to find the individual charge or the individual mass, but he was able to find the ratio between the two so he could get a general idea of the particle's charge and mass. Thomson was able to show that the cathode ray beam contained particles with both mass and charge by finding the charge-to-mass ratio. These particles had an identical charge-to-mass ratio no matter what kind of metal was used for the electrode. This indicated that there was the same small, negatively charged particle found in all kinds of elements. The electron. Later, in 1909, Millikan determined the charge of the electron in his famous oil drop experiment. This allowed him to use the Thompson's charge-to-mass ratio to calculate the mass of the electron. He found the charge of the electron was 1.6 times 10 to the negative 19 coulombs, and the mass of the electron is 9.11 times 10 to the negative 31 kilograms. Example: if a cathode ray beam exposed to a magnetic field of 0.040 teslas requires an electric field of 1.2 times 10 to the 6 newtons per coulomb to remain undeflected, how fast are the cathode rays? In this example, we're given an electric field equal to 1.2 times 10 to the 6 newtons per coulomb, and a magnetic field equal to 0.040 teslas. If an electron is undeflected by these perpendicular electric and magnetic fields, the velocity of the electron can be calculated using the electric field strength divided by the magnetic field strength. This is 1.2 times 10 to the 6 newtons per coulomb divided by 0.040 teslas, which gives us 3 times 10 to the 7 meters per second. Next example. When the electric field is turned off, the same cathode ray beam curves with a radius of 4.26 millimeters in the 0.040 Tesla magnetic field. Use the velocity from the previous example to calculate the charge-to-mass ratio for the electrons. We're given the same magnetic field, which is 0.040 teslas. The radius of curvature of the electrons, when they're in the magnetic field, is 4.26 millimeters, which is 4.26 times 10 to the negative 3 meters. The velocity is the velocity we found in the previous example, 3 times 10 to the 7 meters per second. The charge-to-mass ratio is equal to V over BR. This is 3 times 10 to the 7 divided by 0.04, the magnetic field, times the radius, which is 4.26, times 10 to the negative 3. This gives us a charge-to-mass ratio equal to 1.76 times 10 to the 11 coulombs per kilogram. This is the value, or close to the value, that is always found when the charge-to-mass ratio for a cathode ray beam is determined. It's the charge-to-mass ratio for the electron. Part 3. The gold foil experiment. Ernest Rutherford discovered the alpha particle in year 1900 at McGill University. The alpha particle is a very dense, doubly charged, this means it's 2 times the elementary charge, positive ion. It's later to be shown to be a bare helium nucleus containing 2 protons and 2 neutrons. In 1909, alpha particles were used for the gold foil experiment. In the gold foil experiment, alpha particles were shot at a very thin strip of gold foil. The prediction was that the alpha particles should be much denser than the plum pudding atom. This means the alpha particles should go straight through the plum pudding atom without being deflected, they just go in a straight line. The actual result was surprising. When the alpha particles were shot at a thin sheet of gold foil, many of the particles did go straight through as predicted. However, every once in a while an alpha particle would bounce back, as if it hit something very dense. Rutherford said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back to hit you." Rutherford had to conclude that there must be something very small, positively charged, and very dense in the center of the atom. The nucleus. After this, the models of the atom came quite quickly. Bohr studied emission and absorption spectra and came up with the energy level model of the atom. De Broglie discovered the wavelength of an electron and came up with the electron waves model of the atom. Schrödinger thought about some cats, did a lot of math, and came up with the probability cloud model of the atom, which is used today.